heard about from sections. I think this is one of the things that confuses people even when I don't jack up the notation, right? So the idea of robust regression, just to return to it briefly. By using the L1 norm of the residuals of this vertical error, right, what we get is we get a version of the regression which is less sensitive to outliers because its absolute value of this distance in here that's being pulled around, not the square, okay? And the square would be bigger, and it would really haul stuff over like this. Okay, you may note something here. This guy, y minus the prediction. Why is it y minus prediction? Convenience, roughly speaking, and the way that the terms fall out once we do the first order inner last, and just it's a nice way to do it. It's like you'll see it in stats textbooks this way. But there's literally no problem with switching the order f minus y. There's no difference because things get squared. So if you change the sign, it gets squared. It's still the same sign, right? So the only reason to write it in this order is convention, because stats textbooks tend to do that. Over here, I'm writing it the other way, f minus y. And there's a reason for that. This time, the order matters. Not because the absolute value is any different, but because by convention, what we're going to do next is we're going to take the gradient of this, right? And by convention, the gradient points upwards. To make the gradient point upwards by convention, it's got to be this order. Okay? Otherwise, you get a gradient pointing down, and that's not what we do. Okay, so I have modified this set of slides. I'm going to push the changes to the PDFs so that this is notationally consistent, because this was the wrong order round on this slide last time, okay? And again, what's happening here is that when we have the L1 norm, the absolute value of something, right? What is the derivative of that absolute value? That's going to be our loss function. And it's going to be, you know, if you take the absolute value of x, what you get is positive x when x is positive, and you get negative x when x is negative. That's what the derivative of the absolute value of something is. So in this case, the absolute value of the residuals vector, positive when, sorry, I should do this, the orientation that's going to match. So positive when we're on the positive side of the error residual, negative when we're on the negative side of the residual, right? And so that's why L1 looks like that. This is also, just a reminder to you, this is also why L1 doesn't have an analytic solution, because at that very point where the minimum is a corner. And a corner is not differentiable. There is no defined derivative at this point. So you can't solve for it the way you can here. Here you can solve for the derivative equal to 0. So that's why robust regression does not have an analytic solution, unlike OLS. Okay, and this whole thing here, actually, let me just, nobody wants to look at this, but this thing right here, this was another place where my slides were backwards earlier. And the funny thing is that there were two things that canceled each other. This used to be positive, and this used to be switched, y minus f. This is the correct way. Those two negatives canceled each other out. It still gave the right answer. But this one was doing gradient ascent on the negative gradient. And again, if we set it up this way, by convention, the gradient, this partial, should point, oh, I don't have that. But remember, this is the L1 function, right? So it should point upwards in each case, which means that to go down to the minimum, we've got to go downwards. So this is the correct notation. F minus y gives us a gradient that points upwards. And then we have to step negatively in that direction. This should be a negative sign. Again, the two problems that were here on this slide previously, they canceled each other out and gave the right answer. But it's just going to mess with you in terms of the fact that gradients should point upwards by convention. Okay? Does anybody have any questions on this? And again, I'm going to re-export this. I'll update the slides in the repo so that you have this version of it. Okay. Another thing to note is that I'm slow, right? We are now 1 full day slow on the lecture schedule. So those of you who bothered to come to class in the sun, I deeply appreciate you, and you get to determine the future course of this class. You may have noticed that there is a day on the schedule right before the exam that says review or padding for being slow. So, show of hands. We have two choices on how to handle this. Either I record an extra lecture on one of these weekends between now and the exam, and you've got to watch that entire extra lecture on your own, or I do that to the exam review, right? So they have their pluses and minuses, but that's where we're at. So I don't love doing this to you, but given that this is happening, which way works better for you? I'm going to give you like 10 seconds to think about this. And if you would rather see the extra lecture be lecture, please raise your hand. And if you would rather see the extra recording be the exam review, please raise your hand. That is so 50-50. One more time, the ones that would rather see it be lecture. I can't even tell. It's going to be a coin flip. Okay. I'm sorry. Maybe I'll even work out a way to speed up, but I doubt it, especially given what I just did just now. So, all right. I will let you know which one it is, and I will let you know early next week. So we were talking about decision trees. And decision trees are super fun because there are a bunch of quote-unquote algorithms here. But they're all the same damn thing. They're all recursive. They're all following that recursive algorithm that we talked about. Their only difference is splitting criteria. Every time they make a split, how do they choose it? And what they might do at the end after the tree is built in terms of pruning, right? So we previously were talking about ID3, which is the very, very first decision tree algorithm. C4.5 is an example of a better version of fundamentally the same thing, right? It's still an information gain. It's still an information gain, but it's a normalized information gain. So why is it important to normalize it? This is like super common all across machine learning. It's not just about decision trees. But what happens when you have a training set, which is 9,000 healthy people and 6 cancer patients? Because that's kind of a normal ratio. You're training on an algorithm that has relatively few of one category. What do you think you should do strategically during learning in the case of rare training data? Anybody got some suggestions? Yeah. Sorry, say that louder. We'll get rid of any outliers, but the thing is that we want to accurately predict cancer patients, and we've only got 6 of them, whereas we got 9,000 healthies. So we don't want to get rid of our cancer patients because we want to predict them. Is there another approach? So Bayes' rule is a good intuition. It definitely is a way to do this. And just to remind everybody what Bayes' rule says, it says you might, if you're trying to classify, is a data point a cancerous person? There's two things you should probably look at together. One is the probability of these measurements being cancer. But another thing is the probability of cancer overall. Cancer is a rare thing. So those two probabilities should multiply by each other when you make a judgment about is a particular measurement a cancerous person or a healthy person. Cancer is rare. So even if you see measurements that look like cancer, maybe it's just a weirdo healthy person. Okay? So the Bayes rule intuition, the base rate, the probability of cancer, period, we can scale our answers according to how common a category is, right? If a category is very, very rare, we might want to think about our data point differently than if the category is very, very common, okay? So what is C4.5 doing? Well, it's doing everything that was happening in ID3, this information gain, and then it's normalizing it based upon how common is the category. Okay? Yeah?
So if I can use both these formulas, you like S off the bottom, what is it?
It's the number of things in that data set. So S is always it's a counting number, right? So in these examples, you will see stuff like O, the parent node before we split is S without any subscripts. And that parent node has 3 positive class and 3 negative class. So we're counting up how many positive class or how many negative class or just how many at all, depending upon that notation.
So if your like node after a split is like 3 items, it would be like 3 over 6.
Exactly, right? And if you look back through our slides a couple ago, you'll see exactly that. You'll look and there's that big calculation slide, and you'll see that S of I over S term is out in the very, very front, and it says exactly that, 3 over 6, right? 3 positive class out of 6 total. Okay? Actually, instead of talking about it, I probably should just show it. Where is that? Slide animations. There we go. Right? So here's those cardinalities, the number S of I over total S. Okay? And if you look at number 1, right? Like look at this. There's 1 data point over here out of the 6 that started up here, 1 over 6. Down here on the right-hand side, there's 5 data points. Out of the 6 that started, that's 5 over 6. Okay? So those terms wait like, most of the data's over here, so most of the information's over here. That's why those terms exist. Okay? All right. So the only difference with 4.5 is that we're normalizing so that rare categories can count enough to get predictions off, right? Because you would tend to ignore 6 data points out of thousands unless you weight them differently because they're the only examples you got, okay? So that's what this P term does, is it helps reweight things so that rare stuff can have an impact. All right, so pruning decision trees is something that C4.5 also does. Remember that in trees, regularization is chopping off really deep branches, because really deep branches are fundamentally like weird exceptions to rules, right? If you think of the tree as a rule set, and most of the tree is like level 3, and then there's like this one branch that goes down to level 10, That's like a really twisty-turny decision with a lot of ands in terms of the if statement. It is a really weird exception, and it is probably a weird outlier. So chopping off those deep branches, that is how we can go ahead and say we're regularizing the tree. Now, there are so many different ways to do pruning. You can just prevent your tree from growing too big. So we just have a depth limit. You can do things like deciding on a criterion that's statistical as we are building the tree, not to build any further. Those are two different things, right? Like just saying I'm not going to go deeper than 3 down on the tree. That's a hard limit. It has nothing to do with the data. A chi-squared test, seeing if there's really a difference, right, between my tree post building the next level and pre, that's data-driven, okay? So pre-pruning can be either hard-coded or it can be data-driven. Generally speaking, I'm telling you this for your future self because I'm not going to talk about any algorithms that actually use the chi-squared test in this class, so don't worry about it. 4.5 is a post-pruner. It builds the tree first completely, and then it chops the trees according to a criterion, right? So this is another case where I'm talking to future you, not somebody, this is not anything you got to know to get a test done, okay? But let's talk a little bit about future you so you understand how post-pruning works at least a bit. So we've got some alpha term. And like in the rest of machine learning, these alphas and lambdas, these are little dials, okay? And they're hyperparameters. And we can choose to be harsher with our pruning, or we can choose to be kinder and not so interventionist, okay? So fundamentally, this alpha is a penalty term, okay? And what we're doing is we're trying to find an alpha such that we can find the value of the complexity of each node being the current complexity measurement plus adding in some discount for adding another level, okay? So alpha is a discounting term. That means it's got to be less than 1, okay? It's a number less than 1. It's a discount on doing something. So doing something is going to add to the complexity. So every level we build is going to go from our current complexity measurement, which is R sub t, plus some alpha for these terminal nodes. Okay? So we can set a total alpha value that we don't want our total complexity to be bigger than. And then we can just keep building our tree until we hit this. In scikit-learn, it's called CCP alpha. It's a parameter for pruning. The total complexity cost of building the tree, when it hits CCP alpha, we're done. Okay? We're going to chop it off. So discounting factors, this is like a kind of a weird one, but it is fairly common in reinforcement learning. So if you remember, we talked in the very beginning, reinforcement learning is like a totally different subject than supervised learning. And the idea of reinforcement learning is based on discount factors. It's based on the idea that, okay, it cost me so much to get here. Like, should I take the high payoff reward right now? Or should I wait 10 steps knowing that I will get bigger reward probably then? And then the case is we have to apply a discounting factor to future rewards. Okay? Future rewards are not as good as rewards right now. And so the same kind of math turns up again in other places. All right, again, if you want to dive into it, I literally copy-pasted this out of scikit-learn's docs. Again, scikit-learn's docs, as I've said multiple times, I know people who learned most of what they know about machine learning in those docs. So there's references, things you can pursue if you want to actually understand this on a deep mathematical basis. Okay, the last algorithm I want to put out there, because scikit implements it, and it's the one that you can use for decision tree regression. Did you know that decision trees can make regressors, not just classifiers? So it's called CART. CART uses a different splitting criteria that we haven't seen yet. Any economists in here? Nobody doing economics? Okay. Anybody ever heard of the Gini impurity measure? It's very commonly used in economics as a measurement of inequality. Like, you got a population of people. How many of them are rich? How many of them are poor? How much inequality is there in the population? We use Gini in economics for that, okay? But Gini impurity is actually a lot like information entropy, it turns out. And you can even see that in that it's probability times 1 minus probability. If you logged this baby, it would be probability log probability, right? It would be very close to information entropy. So a few things about CART. It is strictly binary. Okay? You can't have 3 branches off a parent, or 4, or 12. It's got to be binary. And it can be used for regression. So let's compare all these splitting criteria. So here's information entropy in the big black line. As the probability of a binary class goes from 50-50, where we know information entropy is highest, right? The most disorder is, I don't know what's going to happen with the coin flip. It's a 50-50 toss-up, okay? That's disordered. So a 50-50 class is the highest entropy. So if we scaled information entropy, like we see in ID3, then we get the gray line. Okay? So it's just a shortened version of entropy. If we use the Gini impurity, we see this dotted line in red. And if we were just using misclassification error, like how often am I wrong, right? If it's a 50-50 coin flip, it's 50% of the time you're wrong, okay? It's just this. So you can see that all of these things are highly related splitting criteria. In fact, it almost doesn't matter which one you use. If you use a decision tree, you build a decision tree, and you pick all 3 choices of possible criteria, you're not going to get radically different results. I'm just going to tell you that, okay? You're going to be a few percent here, a few percent there. There's really not a strong reason to prefer any one of these over the others. It's merely like, you know, I'm an algorithm researcher, and I'm going to propose a new algorithm, and it's going to be different than everybody else's. It's just, you know, classical, it doesn't really matter stuff. The only big difference between these algorithms is fundamentally, does it do pruning, and how? Okay, a little bit is that ID3 isn't good at handling categorical data. You shouldn't use ID3 for categorical data. But guess what? Scikit-learn doesn't implement ID3, so it doesn't matter. You're never going to be using it in your actual programming. Okay? So really, these are all the same idea. The splitting criteria, they're so similar. The only difference is algorithmic. It's how we prune, how we can handle the data. Okay. So, as I promised, regression can actually be done with CART. And scikit-learn, I just stole this out of the scikit docs, okay? So you can go look at CART regression in the scikit docs. But what the heck is it doing? I guess I want to draw now, so I should turn on my iPad. So it's building a decision tree in the continuous space, where it's splitting up Yeah, okay, no problems. So what it's doing is, you were used to, like, if I'm drawing a picture like this, this is my bad Swiss roll data set, right? Oops, I can't do that. It's got to go up and down, right? Like this would be your decision surface for a decision tree for classification, right? It's chopping up those variables, x1 and x2, where each one of these lines represents a node in the decision tree, right? So that split is that line, and maybe this split is that line over there, right? Sorry, I'm standing in your way so you can't see. Okay? So it's dividing up the vector space with a positive class on one side and a negative class on the other. Well, regression is just the same trick. We're dividing up the vector space. So what we're going to do is we're going to say, I'm going to chop up the vector space at each one of these lines. And what I'm going to do is, inside one of these chunks here, I'm just going to vote for the average. Instead of regressing by like making a line, I'm going to, just like this situation over here, I'm going to piecewise linear the solution. So x values in here all get one y value, one horizontal line. And x values in this chunk get one y value. And x values in here get one y value. And the nature of the decision tree is just that it's learning where to make these splits. That's all. And within a split, it just takes the average, and that's the piecewise linear regression solution. So that green line is a tree of 5 deep, so there's more splits, right? And the blue line is a tree of 2 deep. And let me remove all my bad lines here so you can see it better, right? So it's, you can see that there's less splits. It chops up the x values into fewer parts.
Would you say the green ball was overfit?
I mean, by eyeball, probably, but, the real thing is doing it numerically and looking at the average error, right? So because this is regression, what we're going to do for measuring error is we're going to be looking at, off the blue line, these are our errors. Sum of squared errors, right? So if we measure that for the 2 deep and we measure it for the 5 deep, we're probably going to see something like this. We're going to see our validation curves, right? And so your test set error will always be going down as depth of tree, sorry, I can't spell, depth of tree, that's model complexity goes up. Training set error will always go down. And at some point, validation set error will start to go back up, right? The validation curve. And so just like before, model complexity goes up. Training error always goes down. At a certain point, validation error starts going back up, and this is where you say everything over here is overfit. So your eyeball meter is great, but it's not the actual judge. The actual judge is when does the validation error go back up as complexity goes up. Yeah?
So just to kind of clarify how this regression happens, it's different from OLS, where OLS kind of tries to create this line of best fit for your data.
Mm-hmm.
This essentially is averaging out all the y values within these chunks and just assigning that to every single variable that occurs within that.
You got it. Everything in here is going to be said to be y value 0.5.
So it's just hyper-generalizing all of the data in these chunks by
Yep.
averaging out where they...
And what the decision tree is doing is creating the chunks.
Right.
Yep. So again, just like with This picture over here, what's happening is that it's making a piecewise linear approximation of something that's clearly going to be a more complicated shape. That's what decision trees do. Piecewise linear the stuff. Okay, so summary slide time, right? Here's scikit-learn's thing, decision tree classifier. You can also have a decision tree regressor, as you might guess. And it's going to take arguments, what kind of splitting criteria to use, either Gini or entropy, right? Because entropy will be C4.5. Gini will be a cart regressor. And what it's going to do is it's going to piecewise linear whatever you give it. Right? You can see in this classification, here's the piecewise linear decision boundary. It goes way back up in there, right? And then back over there, and then smacks down this way. Because this, by the way, as you can... You've probably seen the iris data. I'm sorry. I tend not to use that data set because everybody uses it. But raise your hands if you've never seen the iris data. Never once. Okay, so there's a couple. Here's what the iris data is. Some person went in and took a tiny, tiny ruler and measured different parts of different iris flowers, like the sepal length, okay? And the thing is that different iris species are slightly different measurements on average. And so this is a classic classification task where like the entire data set is small enough you can hand calculate things. Because it's hand calculatable, it's why I hate using it in class. But if you look at other machine learning demos and books, you will often see the iris data set. And I hate it. But okay, it's a classification task. Your 3 species are here. Setosa, versicolor, and virginica. Right? And the question is, in these measurements, sepal width, sepal length, right? How can you see the classification between the 3 species? And that's what you're seeing in that. So I'm sorry, I wanted to walk that back so you understand what these figures are showing you. Right? So it's piecewise linear. It is a non-parametric model. It is a recursive model. And something that I really want you to have like right here in the front of your brain is that this model, because look at how these piecewise linear things, they're always parallel to one of the axes. Okay? Like it's either chopping x1 or it's chopping x2. It doesn't go diagonally, not once, because that's the nature of the splitting criteria. Find one variable, x1 or x2, not some linear combination of x1 and x2. Find one variable, chop it at a threshold. So the decision surfaces have to be up, left, down. They can never go diagonally, not once. And that recursive nature of it and that variable by variable nature of it is super important to this notebook that we're about to do right now. Okay? It's got a lot of power. It can overfit any data set. You are going to want to regularize your decision trees. If you don't regularize your decision trees, they will be overfit, I guarantee it. Okay? But they're easy enough to regularize. So it's not really a problem. You can keep them from being stupid. Okay. And fundamentally, it's all about a splitting criteria. So you should probably get this notebook live. Okay? And if you click on the slides, it'll bring you here, and you can open it in Colab. I'm going to use my local copy because you know. So this is while you guys are getting ready, I'm just going to say, instead of the iris flowers, I love using the Palmer penguins data set. I think it's a much cooler data set anyway, because penguins. So Palmer penguins some people went out for years out on the Antarctic, and they were capturing and measuring penguins, like how tall, how heavy, what gender are they, what island did we get them on? So the Palmer penguins data set is something that you can get in a variety of ways, but one easy way to get it is that sklearn are my favorite machine learning and data science plotting library, has that data set in its regular stuff. So you can just load the data set. So you can see here's what it looks like. You've got species of penguin, what island it was taken on. These are categorical variables here, as is sex. We have a bunch of numeric variables: bill length, bill depth, body mass, flipper length. Okay? So the Palmer penguins data set is fun because it's just big enough. So I always tell people that when you begin to look at a brand new data set, you generally want to do EDA on it. Machine learning is no different. You want to explore the data. You want to see, hey, what's the distribution of these variables? Because some algorithms I use are good for only normal distribution of the variables. Some algorithms are great for non-parametric, right? Some of them are good for things that have got weird-ass outliers and highly skewed distributions. Some are not. So you want to know. You want to start off by doing exploratory data analysis. So Seaborn's pair plot, if you're not already familiar from COGS 108, is one way that you can do EDA on a smallish data set. I would never pair plot more than about 10 variables. Okay? It's going to get ugly real fast. But what you're seeing here is bill length on this axis, bill depth here, right? And then over here you see bill length, bill depth, flipper length. So like this one over here is bill length plotted against body mass. Okay? If you're not familiar with pair plot or Seaborn in general, the way it works is you pass it a data set, and pair plot's just going to plot all the columns versus each other. Okay? That's what it's going to do. You can color by species or any other variable column that's in there. Okay? So you just tell it if you want to color by species for a data point, whether it's whichever species. Okay? These distributions are showing you the histogram of bill length just for the Adelies, just for the Gen 2s, just for the chin straps in the yellow, right? So the diagonal is just one variable versus itself. The off diagonals are variable versus variable. Super useful, okay? If your data set is too big to pair plot because it's 200 columns, it can still be worth like subsetting down to like say 10 that you think might be important and pair plotting those. Okay? Just a little thought. Always start with a little bit of exploratory data analysis. Okay, so here's your first exercise. Hopefully you're all open and ready, because I need you to remind yourselves how to do train test split. So if you can code that up here so we can get moving, let's do that. We need to create, out of these 300 some lines of penguins, 333 penguins, we need to break off a chunk of them for test set purposes. If you need to be reminded, scikit-learn train, test, split. My favorite is just to copy and paste, yo. So once we've done that, we will see that we have a training set of 223 penguins and a test set of 110 of them. Okay, so this is how we will get a decision tree classifier. From scikit-learn.tree, import decision tree classifier. As always, what this guy is it's an object. You can go over here and note that we have the first argument is what's our splitting criteria. Note that it defaults to Gini, right? The Gini impurity. That's the default if you don't tell it one. Okay. The default max depth is none, but if you want to stop it from growing beyond a certain level, that's an argument. Okay, these are interesting. These arguments say, all right, how far am I going to grow my tree? I could just chop it at a depth, or I can use different criteria. So one thing is, how many samples should I have in a leaf? If there's only one sample in a leaf, that means there's just one class by definition, right? One sample, got to have one class. So here's a hint. If you have one sample in a leaf, it's probably overfit, right? So what if we force, we don't go any further than 5 samples in a leaf? Okay, then we know that we might have some impurity at that level potentially. And if we have some impurity, some mix of classes, then we're probably less overfit at least. So you can choose a lot of different ways to control the complexity. You can figure out the minimum samples in a leaf. You can maximum number of leaf nodes. Never split if you don't get at least this much impurity decrease, right? H of S of the parent minus the sum of the H's of the children, that's the decrease. So if my split would go less than that much decrease, don't split, okay? There are so many different things in here. I am not a good guru with decision trees. I don't have here's my rule of thumb on how to do this. I see a lot of people out there just pick a couple of favorites that they get used to and they kind of have intuitions for. I don't think, to my knowledge, that there's an obvious winner or loser in these different ways of controlling the tree. So just FYI, you can choose whatever you want and try a few of them at least. You should note that some of these conflict with each other, right? So if you have minimum number of leaves, minimum number of samples in a leaf is 6, and the max depth is 3, there's no guarantee those align, and you don't know which one is going to chop you off first, okay? So they're not they're kind of, I would almost think of them as either ors. I wouldn't really try to use multiple ones at the same time. That's my take on the matter, because you just don't know what you're going to get. All right, so by this point, you'll have maybe realized that you need to fit your training data in this next cell. And I know that this should be super, super easy, right? How can we take a scikit-learn estimator model and fit the training data on it? Here's a hint. It's the same no matter what the estimator is. It doesn't matter that this is a decision tree. All scikit-learn estimators work this way. Anybody remember? Who can tell me what to write here? Same as OLS. Yeah? Louder? Model.fit. And what do we pass as arguments to .fit? Right? That's it. It always looks this way. Scikit has a uniform interface. It doesn't matter that this is a decision tree classifier or an OLS regressor. It's always .fit. Yeah. That was a question? That was the thought process happening in real time. Okay, so once we've done this, we've built our decision tree. That's it, it's done. Okay? We've also, at the same time, we've got our predictions on both the training set and the test set. So the predictions on the training set can be used to give us our training set error. Our predictions on, because where the predictions don't match the truth on the training set, right, that's training set error. Our predictions on the test set are for our test set error. So let's introduce a brand new scikit thing I haven't shown you yet. There's lots of different ways to understand how good your thingy is, whatever your thingy is. For classifiers, one thing that you're probably going to want to start with is that there's this thing called a classification report. So from scikit-learn metrics, measuring how good we are is always going to be in metrics. Okay? There's a gazillion metrics in scikit-learn metrics. There are different metrics appropriate in different things. But hey, accuracy score, we probably know what that is, right? And this classification report are two good places to start. So let me just note for you the way every single thing in scikit-learn metrics works. It takes two arguments. The accuracy score is right here, right? The first argument is the truth, the ground truth. This is what the actual classes are. The second argument is what you predicted. It's what your classifier says it should be. So y_train is our estimated classes. Y_train is the truth of the classes. Whoops. Oh yeah. Test set error. I didn't even notice that, right? So do that same thing that you did for training error, but do it for test set error. Okay, so I'm going to give you the hint that you want to copy and paste training set error, accuracy score. But what should you change about that line? Yeah?
Traits test.
Yeah, you want to change all the places it says _train to _test, right? It's not rocket science, but I want you to get familiar with this and do it. Just watching me is not going to help cement the skill. Doing it will help cement the skill. I know it seems lame, but okay. So here is our output. So using accuracy score, we can see that our training set accuracy is perfect. Our decision tree is overfit, right? Because perfect training score is almost certainly overfit. You know there's noise in the data. And that's borne out by the fact that our test set accuracy is only 95.5%. Okay? So as usual, test set accuracy is lower than the training set accuracy because we're overfit on the training set. This is totally normal. It's going to happen to you most of the time. Okay, so yeah.
Even though that's about 95% isn't that still really high?
It's still really high, but it turns out that the penguin classification task is pretty easy for a decision tree. And a new set of penguins might look a little different. We might get slightly lower, but it's going to be in this neighborhood. So yeah, so that was us using the accuracy score. So there are multiple metrics, not just accuracy score, right? We mentioned briefly when we talked in one of the pre-lectures stuff like Hamming distance, okay? Or L1, right? Mean squared error. There's all these different metrics that are going to be appropriate for different purposes. If you look at scikit-learn, dot metrics, you will see the gigantic list of possibilities, okay? Here are all the metrics. And again, every single one of these beasts all works the same. You pass it first the truth, and then your prediction. Yeah?
So I just had a question about I ran the next one to
Yeah.
the whole tree. Something that I'm just kind of struggling to understand here is how these criteria get formulated by the program itself. Because clearly, like with what we've gone over here, we haven't set any criteria, like any split criteria whatsoever.
Yeah. So there's a whole bunch of auto stuff built into decision tree classifier. It auto-magically picks a lot of stuff for you.
So it's like all of that criteria and all of your classification, all of the lines is done by the classifier. Like obviously it's default here, you can mess with it or not, but that's all contained within that.
Yeah, when you call dot fit, at that moment you call dot fit, it makes a bunch of choices and makes a decision tree. So here's what's going to happen. You should explore this notebook further. I want to point